the last lecture, I gave you a qualitative description of what is meant by gravitational potential energy. You take an object, for example, and you lift it through a vertical displacement. When you do, as we'll see, the work done by gravity is negative mgh, where h is that vertical displacement. This then becomes the potential energy of the object because the work that you do against the force of gravity, positive mgh, is the minimum amount of energy that you need to use to overcome gravity. That potential energy then is transformed into kinetic energy as the object falls. The object's kinetic energy, the instant that it returns to its original height, is exactly equal to the potential energy that I gave it in the first place by doing work done against gravity. How do we then describe this mathematically? And then ultimately, how do we arrive at a statement of what is called conservation of energy? Here's how we do so. Okay, so an object is lifted through a vertical displacement. And that vertical displacement, that height change, is always referred to as h. So then therefore we can calculate the work done by gravity in the following way. Now the gravitational force vector is of course always straight downwards like so, and the displacement vector delta r, which is equal to h in this description, is upwards. Notice that there's a 180-degree angle between those two vectors. So as we learned earlier in this unit, when we calculate the work done by gravity, it would be a negative number. So the work done by gravity is equal to negative mgh. Okay, now by definition, the work that I would then do against gravity is the opposite of this quantity. Here's how we write that. So the work done against gravity, and you have to be careful with your phrasing here, by the way, is equal to, by definition, the negative of the work done by gravity. So showing all of the negative signs here, this is the negative of negative mgh. This is positive mgh. And this minimum amount of energy that I use to overcome the force of gravity, the work done against gravity, this then becomes the potential energy of the object at the height h above the ground. Potential energy is always described by the letter capital U, like so, where capital U is then therefore the object's potential energy. So then here's a simple diagram of the situation when you lift an object and then drop it from some vertical displacement, from some height. Let's say, for example, that right here is the ground, like so. And then I take the object here, it has a mass m, and I give it a height h above the ground. The potential energy is equal to mgh as we just described. And then as we say, that potential energy transforms into kinetic energy as the object falls. So let's say that the object then reaches the ground like so, and the instant prior to striking the ground, it has a speed v. This then means that it has a kinetic energy k. The amount of kinetic energy that the object has, the instant that it returns to its original height, is exactly equal to the potential energy that I gave it in the first place. So the potential energy U then therefore is equal to the kinetic energy k. This right here is a statement of conservation of energy. Think of conservation of energy in the following way. Whatever forms of energy that you start with on the left-hand side of my expression is equal to whatever forms of energy that we end with on the right-hand side of the expression. So then therefore the total amount of energy is always the same number. So this statement right here is a simple statement that says that the energy is conserved. The total amount of potential energy that we start with is equal to the total amount of kinetic energy that we end with when the object returns to the ground. Okay, let's use this expression here for two simple examples. In the first example, we'll just drop an object from rest, and then the second example, we'll throw an object upwards initially. Okay, let's go ahead and copy down the first of these two examples. Let me read it to you here. Okay, an object with a mass of 1 kilogram is lifted vertically to a height of 2 meters. In part A, we're going to calculate the potential energy. And then in part B, if the object is dropped from rest, what is the kinetic energy when the object returns to its original height? That is when it returns to the ground. And then in part C, we'll use the formula for kinetic energy to calculate the object's speed. Okay, I'm going to go ahead and use this diagram here to illustrate this example because this example here is basically described by the diagram. And then here's what we're given. Okay, so we're given that the mass of the object M is a kilogram, and the height h is given to us as 2 meters above the ground. So in part A of the problem, we can now calculate the potential energy U. So the potential energy U is equal to mgh. Let's go ahead and multiply this out. When we do, we end up with an energy in terms of joules. Okay, so I just simply have 1 kilogram times 9.8 meters per second squared, and then multiplied by a height of 2 meters, and this is 19.6 joules. And then I release the object from rest, and then therefore the kinetic energy that the object has the instant that it returns to its original height, that is the ground, it's exactly equal to the amount of potential energy that we started with. So then therefore in part B of the problem, the kinetic energy when you return to the ground is exactly the same number. So then therefore the kinetic energy K is 19.6 joules. So what I'm illustrating here in parts A and B of the problem is that one form of energy here on the left-hand side of the expression becomes another form of energy on the right-hand side of the expression. And then lastly, for part C of the problem, let's go ahead and use the formula for kinetic energy, that is this expression here, to find the speed V of the object. So we already know that this side of the expression is 19.6 joules, and now we just solve for the speed V. So let's cross multiply the 2 over to the other side, divide by the mass M on the other side, and then take the square root of both sides. When you do those couple of minor mathematical steps, you then end up with the following expression. Like so. And now I'll go ahead and plug in the numbers, and when I do, I'll end up with a speed here in terms of meters per second. Now I still have the kinetic energy K here of 19.6 joules still in my calculator, so multiply by 2 and then divide by 1 kilogram, take the square root of all of that. And the speed then therefore of the object when it returns to the ground is about 6.26 meters per second. So, okay, and now in the next example, let's basically do the situation backwards. So what I'm going to do here is erase the board, and then I have to move the file on my screen. So let's go ahead and get rid of all of this. Let me now go ahead and take a look at the problem itself. So the second example here is done basically backwards of the first. Copy it down into your notes as I read it here. Okay, an object is thrown vertically upwards from the ground. We'll say it starts from the origin with a speed of 20 meters per second. To what height does the object rise? In this case, we start off with all kinetic energy at the bottom, and that then transforms into the same amount of potential energy when the object rises to its maximum height. So think of it like this. Okay, so here's the ground for reference, and we'll start off here with our object of mass M, and it's initially thrown upwards with a speed V0 of 20 meters per second. It then reaches its maximum height like so, and when it does, we have an unknown height here, h, that we're asked to find. In this case, you could write the conservation of energy here backwards of what we did in the previous example. In this case, all the kinetic energy K that we have at the bottom, this then transforms into the same amount of potential energy U at the top. That is when we reach our maximum height. Now, the only number that we're given here is the initial speed, V0, and nothing more than that. However, let's go ahead and plug in the formulas for both kinetic energy and potential energy into this expression, and then let's see what happens. Okay, so all of the kinetic energy at the bottom, 1/2 m V0 squared, turns into the exact same amount of potential energy at the top, mgh. And then notice that the mass m cancels from the expression. That is like so. And now if I just divide the g to the other side, that will then allow us to calculate the height h. So the height h is then therefore going to be V0 squared divided by 2 times g when you do the math. Once again, I take the g here and move it down to the denominator on the other side of the expression. So then numerically, all that I have is 20 squared in the numerator, that's 400. And then divided by 2 times 9.8 in the denominator, and this then gives me a height of about 20.4 meters above the ground. Like so. So these two opening examples here are a nice, easy illustration of the conservation of energy. First of all, when taking an object and just dropping it from some height, and then secondly, throwing it upwards. Okay, the next two examples that we'll take a look at those two examples in the next film.